what if one factor that could like result in like even done elsewhere? If there's a lot of because you won't make it. I mean, it's new. I don't know. It's like that is actually class. Everyone's having people. My doctor might have said it's 20%. It was still in the box and the fast market. Yeah. I said that it's like. And no, he got it a little bit. It was like confetti in this too. It's like that was that. And that's like give your card value.
Okay, page 15 in your packet.
To me, I said there's something late, but I was like, thank you. Well, like sat there and I was like, I mean, this is about far. Like it's not like.
Okay, so I'm gonna have us, I'll walk through the 2019 FRQs. Number again, 1 and 2 are the calculator, and 3 through 6 are non-calculator. So if you guys are ahead, continue working or you can kind of just follow along with what I'm going through here. Okay, so fish enters a lake at a rate modeled by the function E, given by E of t. Again, your calculator, always make sure you're in radian mode. Fish leaves the lake at a rate modeled by L, given by LT. Both E of t and LT are measured in fish per hour, so you're given the rate. So how many fish enter the lake over the 5-hour period? You know that you take the antiderivative of that rate, you can accumulate that rate from fish per hour into the number of fish. So part A is usually a little bit simpler. So in your calculator, enter in your E of t. So these numbers to the right are this is this is my my guesstimation in terms of how many points each part is worth. So remember, every FRQ is worth 9 points, and so you know, every part is usually between 1 and 4 points. So like, you know, usually if it's A through D, you know, the most challenging portion is or the portion that requires more work is usually more points than ones that are less. So usually A and B are easier, but it's also worth less points. Okay, part B, what is the average number of fish? Average value theorem can get you there, right? So 1 over B minus A, integral from A to B. So our A and B are 5 and 0. So really just taking, but remember, we're dealing with a different function here. The average number of fish, average rate of fish leaving per hour. So we have to use the L of T function. Make sure we put that 1/5 in front. Yeah.
If you would get like 20 fish. 30, yeah.
Yeah, you could, but if it's not a calculator, I would say definitely leave it like that. But if this calculator, I would just go ahead and clean it up. But yes, I think you would get full credit here as well. So even though we pushed it through the integral notation, we're still sitting at fish per hour because we're still dividing by 5. Okay, so we took the integral, but then we're dividing, so we're back to where. So whenever you do average value theorem, you're always going to end up with the same units that you started with.
Can you get like half a point for say B, you put like the number within the units for wrong, would they give you like 1 point? Or when is it just like 2 or no points?
It depends every year. You know, whenever they decide the scoring, they always train the writers or the graders exactly how the points are distributed. But yeah, it wouldn't make sense if it's worth 2 points that one would be the answer and the other would be their units.
Okay.
Yeah, but it could change from year to year depending on what they decide for that year. And also, I'm putting more information on these FRQs than what you need to put down. So I'm putting a lot of indications and reminders. So you don't have to write out nearly all the things that I'm writing out. I'm just, you know, a lot of times I'm writing out the notes so that I can kind of explain the process. Okay, part C, at what time is the greatest number of fish in the lake? Okay, so we know this is extreme value theorem, but we first have to create a formula that will allow us first to get to the total number of fish and also finding the derivative. Okay, so this is the rate in, rate out problem. So I'm going to start off with building my formula that will tell me the number of fish at any moment in time. So I'll use f of t to represent the number of fish at any given time. So total amount equals initial plus amount added minus amount removed. We've seen that formula for these rate in, rate out problems. So initial number f of 0, the number added from 0 to t, whatever that t is of e of x. E of x is the rate at which fish is entering, and L of t is the rate at which fish is leaving. I'm using a different variable here because the integral from 0 to t, we mentioned that t will replace that x. But I just want to have some formula that I can build from. So then if I want to find the derivative, because I know that for extreme value theorem, I need to find endpoint, I need to test endpoints and critical points. The endpoints and critical points are going to go into my original formula. But to find the critical points, I have to set my derivative equal to 0. So I'm going to build my derivative f prime. F of 0 is 0. Derivative of this expression will turn it into e of t, right? This integral goes away to e of t minus L of t. So then my formula is just f prime of t is equal to e of t minus L of t. That's my derivative equation. I'm going to set equal to 0. So with extreme value theorem, I'm always finding the derivative and setting equal to 0 to find my critical points. And I'm just graphing this function here. I'm graphing this e of t minus L of t, looking to see where that graph crosses the x-axis. Cross the x-axis at 6.2035. So we have 3 t values to test. We got to test t equals 0, t equals 8, and then this critical point t equals 6.20356. And we're entering all 3 values into my f of t so that I can compare the number of fish at those hours, at 0 hour, 8 hours, and then at 6.2 hours. So we know that there's 0 fish in the pond to begin with. So that's easy. To find f of 6.23, we just do 0 plus, and then the integral from 0 to 6.2 minus integral from 0 to 6.2 of L of t. That's going to give me 135 fish. F of 8, 0 plus integral from 0 to 8 minus integral from 0 to 8 of L of x. I get 80.9. And if I compare these 3 numbers here, 135 is the largest amongst these 3 numbers. So by EVT, the greatest number of fish is at 6.203. Okay, hopefully we've seen enough of these rate in, rate out problems to kind of feel comfortable with the pattern to step through these problems like these. Part D, the rate of change in the lake is the rate of change in the number of fish increasing or decreasing. So you notice the word rate of change. This is already at the fish per hour level, but it's asking for the increase or decrease of that rate. So we know that E of t and L of t are at the rate level. So if I want to find the rate of change of that rate, I got to do the derivative. So we know that the rate of change at which whether the number of fish, the rate is increasing or decreasing, is going to be E prime minus L prime, right? The rate at which fish is coming in minus the rate at which people, the rate at which fish leaving. So F double prime, since F prime is E of t minus L of t, F double prime is going to be E prime minus L prime. So we're just building off of this first derivative to build my second derivative. Once I get to my second derivative, just plug in 5. And it was fish per hour, but now it's going to be fish per hour squared. It's a negative, so this negative tells you that your rate is decreasing. Right, number 2, velocity of particle P moves along the x-axis given by a differentiable function, where velocity is measured in meters per hour and P is measured in hours. Select the values of V of t. Velocity is shown. Particle P is at the origin at time equals 0. Justify why there must be at least one time between 0.3 and 2.8 where the acceleration of the particle is equal to 0. So we know that acceleration is the slope of velocity. So if this is the velocity graph, can you imagine a point where the slope of this velocity graph is going to be 0? So if you were to sketch out this graph here, right? So at 0 hours is 0, at 0.3 hours is 55, then it goes to negative 29, goes back up to 55 and 48. So if you were to sketch this graph, right, there's got to be at least a slope 0 somewhere between. And the reason that we know that is because we have 2 points that are exactly the same. If 2 points are exactly the same, then we know that somewhere between it's got to go up, or it's got to go down and come back up, or go up, come back down. And along that process, we're gonna have a slope 0. So can you guys recognize which theorem they're trying to get us to use? Rolle's theorem, yeah. So because my velocity function is continuous on the closed interval and differentiable on the open interval, my slope between the endpoints is going to be 0. If I can create a 0 slope between 2 endpoints, I know there must be, the graph must have a slope 0 somewhere between as well. Part B, use trapezoid sum with 3 subintervals to approximate. So trapezoid area, make sure you memorize this. 1/2 width, height 1 plus height 2. Your width information comes from the first row. Your height information comes from the second row. So within each subinterval, you can subtract the x values, the t values, to get the width, 0.3, 1.4, 1.1, and then your height is going to be 0, 55 for the first trapezoid, 55 minus 29 for the second trapezoid, then 29 plus 55 for the third trapezoid. One half width or width over two, either way. Okay, part C. Second particle Q also moves along the x-axis so that its velocity between 0 and 4 is given by v of t. You see there. Find the time interval during which the velocity of the particle is at least 60 meters per hour. And then find the distance traveled on that interval when the particle is at least 60 meters per hour. So we have to create a formula that represents that. So at least 60 means 60 or more. So we want to figure out where is my velocity graph going to be greater than or equal to 60. Okay. So to make this a little bit easier to work with, I'm going to subtract 60 over to the other side. I'm just going to look for where is v of t minus 60 greater than or equal to 0. I'm going to graph this expression and just see where the x-intercepts x-intercepts are. So I want to see, and once I graph it, that's something like this, between 1 and 3.5. This is the region that I care about, right? The region that's above the x-axis. I first need to figure out the boundaries. So if I were to graph v of t minus 60, look for the x-intercepts, I get 1.866 and 3.519. And then between those time intervals, my graph is above the x-axis. So if I can take the integral, I can find the displacement. I can figure out how much distance I traveled in that time period when I'm traveling at 460. So we do the depth integral from 1.8 to 3.5 of v of t. Make the calculator find that for us. So the distance traveled with those restrictions is 106.108 meters. And part D, at time t equals 0, particle Q is at x-axis, location x equals negative 90. Using the results from part B and the function v of q, approximate the distance between particles P and Q at times t equals 2.8. So we're going to have to track both of these particles separately, figure out where they begin, how much movement they made, and then at 2.8, we can compare their distance, compare their locations. So let's start with particle P. Particle P starts at 0. Okay. So again, we really use this final equals initial plus displacement formula a lot. So if I want to find my final location of particle P, I know I'm starting at x of 0. I'm going from 0 to 2.8 of v of t for particle P. So location, I'm starting at 0. In this time period, I move 40 units to the right. So we end up at 40.75 on the x-axis. For particle Q, I'm starting at negative 90. Okay. And then between 0 and 2.8, I travel 135 units to the right. I'm going to end up at 45.9376. So then I compare these two, how far are they apart? The distance between the two particles is 45.9 minus 40.75, around 5 meters. Okay, number 3. Okay. Now we're moving on to the non-calculator sections here, 3 through 6. Continuous function f is defined. The figure above shows a portion of the graph consisting of 2 line segments. Yeah, 2 line segments and a quarter circle here, centered at the point 5, 3. So, sorry, quarter circle is here. And imagine this is a kind of quarter circle that's up here. Centered at order pair 5, 3. It is known that point 3, 3 minus root 5 is on the graph, so I just identify that order pair that sits on the curve. And then 5, 3 is here, so this is the center of this imaginary circle here. Or you can imagine the quarter circle kind of forming right there. Okay. So part A says the integral from -6 to 5 of f(x) is 7. Find the integral from -6 to -2 and show the work that leads to your answer. All right, so we know that integral from -6 to 5 is 7. Find the value from -6 to -2. So we know from -6 to -2 is kind of this unknown region. But we do have a known region, which is from -2 to -5. So I'm going to create a formula that I can kind of build off of, right? I know that the region between -6 and 5 can be broken into from -6 to -2, which is part of the graph I see, with the graph I do see, -2 to 5. So I know this is 7. I can figure this out using geometric shapes and adding them up, and that will help me figure out my unknown that I'm looking for here. So the work that we have to do is trying to figure out that area from -2 to 5. So let's go to our graph here. So from -2 to 5, you got a combination of triangles and this region. That region that is not a geometric shape, but we can find that area using the difference of two shapes. We got a triangle here, 1/2 base times height, 1/2 base times height. 1/2 base times height. Now, you may see some other shapes here, but just keep reminding yourself that the only area that you care about is what's between the graph and the x-axis. If you see shapes elsewhere, it's not part of our discussion. So make sure that you're only looking at what's between the graph and the x-axis. So triangle here, triangle below, triangle above. Here I did a square and I did a triangle. I guess you could just, yeah, I split up into smaller parts, but as long as you can identify all the different regions. And then for this region here, this is the result of a square minus a quarter circle. So my square is 3 times 3, which is 9. My quarter circle is 1/4 pi r squared. So 9 minus 9 pi over 4. So if I add all that together, 1/2 minus 1/2 minus 1/4 plus 1/4 plus 2 plus 9 minus 9 pi over 4, I get 9 pi over 4 minus 4. So that is the result of negative integral from -2 to 5. So if I do 7 minus this, 7 minus 11 minus a negative 9 pi over 4, I get this 9 pi over 4 minus 4. That's the unknown region that I don't see that's cut off from my view. Part B, evaluate the depth integral. This problem will be a lot easier to work with if you understand that we gotta do two separate processes here. Let's split this up. There's an integral rule for f prime, and there's an integral rule for 4. So one, we have to leave it in the function notation. The other, we can use power rule. So I'm gonna split this integral up into 2 problems. I split up into 2, integral of f prime, and then the integral of integral of 4. So we don't have the f prime graph in front of us, but we can use first theorem to make f prime turn into f of x, and then we can plug in our upper and lower bound, f of 5 minus f of 3. F of 5, we can tell by looking at the graph, is 0. F of 3, they tell us at the beginning that y value is at 3 minus root 5. And then the integral of 4, we can just go through power rule. 4 becomes 4x. Plug in my upper and lower bound, I get 20 minus 12, which is 8. So I add all that together. Again, without a calculator, best I can do is say 2 plus 2 root 5. Part C. The function g is given by g of x is the integral from -2 to f. So if I were to work this down, g prime, this is going to be f. So my f is now I need to consider f as my g prime graph. Find the absolute maximum. So I got to go through EBT between -2 and 5. So I know I have my endpoints between the -2 and 5. My critical point is going to be at 0.5. Because that's where my x-intercept is, right? So now I got to think of this as my derivative graph above and below, positive slope, negative slope. So, sorry, my critical points is at -1 and at 0.5, and then at -2 and 5. So above is positive slope, below is negative slope. So if I want to find absolute max, I'm going to test my endpoints. I'm also going to test my -1. I don't have to test 0.5 if I don't want to, because it's a relative minimum. There's no chance that can be an absolute max. So f of -2, sorry, integral of from -2 to -2, that's 0. -2 to -1, that's 1/2. -2 to 5 is 11 minus 9 pi over 4. Part D. You got a limit problem here, but if you plug in, I'm looking at this thinking, oh, maybe this is a L'Hopital's rule problem. But when I plug in, I'm able to get a real number, so it's just asking me to evaluate. Remember, we don't do L'Hopital's rule unless you get a 0/0 in return. So by limit, I'm just plugging in 1 into my expression. 10 minus 3, f prime 1. F prime 1 is 2. Arc tangent of 1. Okay, so what that means is saying, where's tangent first going to be equal to 1? Right, where's tangent first equal to 1? That's going to be at 1. So speaking of which, make sure you review your unit circle values, right? Because that's something that they can throw at you on the AP exam. So make sure you go back and at least, at least first quadrant, right? But it'd be best if you just know all your unit circle values. You don't clean it up all the way as far as I did. You can leave it in complex fraction. That should be fine. Right, number 4, related rates. Okay, cylinder here. If you see a cylinder, you have to keep reminding yourself that cylinder is an easier shape to work with than cones. Right? The formula looks the same, but the nice thing is that your radius is constant. So if you know what your radius is, you just quickly remove that radius r variable and move forward with the problem. So ignore the top here. This is going to be part C. Okay, so a cylindrical barrel with a diameter of 2 feet. So diameter is 2, you know your radius is 1. Collects rainwater, shown in the figure. The water drains out through a valve, which is not shown at the bottom of the barrel. The rate of change of the height of the water with respect to time is dH/dt. So that's the rate at which water is coming out. Here's the formula, B equals pi r squared h. Looks a lot like cylinders, sorry, a lot like cones, but a lot easier to work with. Find the rate of change of the volume of the water with respect to time. So there's the related rates here. So we want to find dV/dt, but before we do that, we know that our radius is a constant, so we can just quickly get rid of that radius variable and then just start off with v equals pi h, right? Because my radius squared, 1 squared is 1, that goes away. So I can just find my related rates derivative starting at a relatively easy equation. So v becomes dV/dt, pi stays, h becomes dH/dt. Okay. They tell us that dH/dt is -1/10 root h, so I can replace that from the problem. H is 4, I can plug 4 in, solve for dV/dt. I get -2 pi over 10, which is -pi over 5. Your units of measure, volume is cubic, so cubic feet per second. Is the rate of change of the height of water increasing or decreasing? So we have the HDT, we just plug 3 in. Oh, wait, hold on, let me see. Oh, my bad. Is the rate of change increasing or decreasing? Okay, so we got to work our way down to the second derivative. It's not just asking, is the rate increasing or decreasing? It's asking, is the rate, sorry, it's not just asking if the height is increasing or decreasing. It's asking if the rate is increasing or decreasing. We have to work our way down to the second derivative. So dHdt is -1/10. I converted that h to the 1 root h to be h to the 1/2. I'm going to find the derivative again. So dHdt becomes d2h over d22. -1/10 stays. I go through power rule. 1/2 h to the -1/2. Again, change related rates. So h becomes dHdt. So now this is my second derivative function. Replace dHdt with -1/10 root h because I know that's my expression from what dHdt is given to me. Clean this up, the root h cancels out. I get 1 over 200. That's a positive number. So I know that my rate is increasing. So therefore, since the second derivative is positive, we know the rate of change of the height of water is increasing since the second derivative is positive. Okay, part C. Separation of variables, so we're going to cross multiply, solve for h. Remember, h is a dependent variable, so we want h is on the left and t is on the right. We start here, and I show my work up here. Okay. Cross multiply. I got my h's together, got my t's together, everything else together. Brought that root h up to the top with your power rule on the left and the right. Solve for c. Once I solve for c, I turn around and try to figure out how to get h by itself. Okay, let's do one more, number 5. I feel like number 6 is pretty straightforward. I think you guys can work through that. But I think I want to go with number 5. I want to make sure I can go through a full problem involving area and volume. And again, keep in mind, non-calculator. So let R be the region enclosed by the graph of G and H. Find the area of R, so area is top minus bottom, but we got to do this by hand here, so. The top graph is the 6 minus 2, x squared minus 1. The bottom is the -2 plus 3 cosine pi over 2x. So quite a lot of, it's not hard to set up, but it is quite a lot of work because we don't have a calculator in front of us. Okay, so it's good to practice through these steps here. Kind of refreshing our memory in terms of how we can expand everything for power rule, how to deal with use substitution, and then also keeping in mind how to, remind ourselves of unit circle values. So not hard, just tedious. I'm going to expand all this out. Actually, I went through use substitution, but I could have expanded it out on the left side. And then here, 3 cosine of pi over 2x. I definitely want to go through use substitution. My u value is pi over 2x. Du dx equals pi over 2. Solve for dx. Dx is 2 over pi du. Push that 2 over pi out in front, 6 over pi. Cosine becomes sine. Plug in my upper and lower bounds. And make sure that you don't leave your answer with sine pi and sine 0. You got to convert those back down to numbers. You can leave your answer unsimplified in terms of this, but you can't leave your answer with sine and cosine showing. You got to resolve those values. Part B says region R is the base of a solid. For the solid, each of the cross section is perpendicular to the x-axis, has an area of 1 over x plus 3. So normally with cross section, we have to build the base, and from the base, we got to build the area. But here, they're already telling you what the area is. So we can just skip all that first 2 steps and just take the integral of the area, right? There's already 2 dimension. You put the integral around it, it gives you that 1 over x plus 3, or that gives you that volume. So they say cross section here, but really, you're just setting it up. You're not even doing a lot of the steps from most cross section problems. So relatively simple integral problem. Use substitution, upper and lower bound, natural log of 5 minus natural log of 3. This is sufficient, or we can break it down even further. Either is fine. Part C. Right, but do not evaluate an integral expression that gives the volume of the solid when R is rotated around the line y equals 6. So here I drew at the top here. Y equals 6 is clearly above the curve. And there's a gap. So we know this will be Washer method from the axis revolution. Axis, we got to extend to the furthest boundary. From the axis, extend to the closer boundary. The longer radius is your big R, smaller R is your little radius, is your little r of x. Top minus bottom, 6 minus g of x is my big radius. 6 minus h of x is my little radius. And then just set up using Washer method. Pi, integral from 0 to 2, big radius squared minus little radius squared. That's all we need to do. No need to do anything more. It's just the setup. Okay, I'll leave for 6 to 2 on your own. Again, in the mornings and afternoon, I'm working through packet 6. Tomorrow we'll work on the 2018 FRQs. All right, come get your phones. No, you're right. This one is an overestimation. I made a mistake, like the
Okay,
overestimation, you're right.
that was like, that's why I was thinking it.
Yeah, I'm glad you caught that too.
Oh, one more thing.
Mhm.